Hello everyone, I am Mr. Sunil Kumar, Assistant Professor in the Department of Mechanical Engineering at the esteemed AJ Institute of Engineering and Technology, Mangalore. Dear students, I am teaching you on the lab, material testing lab for 4th semester mechanical engineering students as per video syllabus. In this lab particularly, we are studying about the properties of materials. It is required to know and understand the different properties of materials because materials in real-time applications depends on the properties, their stability, and also we need to understand the different types of failures that may occur which depends on the properties of the materials. Among the properties, we have dealt with number of properties such as impact strength and direct shear stress or shear strength of the material. In this class, we shall learn about the torsion, the pure torsion, and the torsional strength of the material. What is torsion? Torsion means whenever any structure or any specimen is twisted with respect to its axis, then it is called as torsion. Generally, any shafts which are rotating will be subjected to torsion because it is rotating with respect to its axis of concentration. There will be change in the material deformation. The material will deform in circular shape, in the circular path. So this is known as torsion. And we have to understand about what is the torsional strength of the specimen or the material. How much load it can withstand when such twisting load is applied. That we will study about in this experiment. Once again, the material taken is mild steel. This test is conducted in torsion testing machine. We will find modulus of rigidity as we have found modulus of elasticity in tensile testing. Similarly, we will find modulus of rigidity in torsional testing. Then we will find modulus of rupture means failure, that is breakage. And then we have found tensile yield strength in tensile testing. In torsional testing, we will find torsional yield strength. What is the procedure to conduct the specimen? We have to measure the diameter of the bar. We have to measure the diameter and its length. And we have to draw one line parallel to the axis to identify the amount of twist that is happening after the application of load. Next, we have to insert the specimen in two grips of the machine. Select suitable scale. A suitable scale is selected for different types of materials. For mild steel, it will be different. For very hard materials, the scale will be different. We have to apply torque by hand up to 10 degree of angle of twist. Note the torque and the angle of twist. Then we have to apply torque by using machine, that is motor. So we have to take the measure of load applied for each 2-degree interval of rotation. There will be graduations for the rotation in degrees. For each 2-degree interval of rotation, we have to note down the load. Then at a particular point, there will be yield load, that is the needle in the dial will stop at a particular point, mentioning the yield of the material. Then we have to note down that yield load to calculate the yield torsional yield strength. After that, we have to plot, as similar to the tensile testing, we have to plot the torque which is obtained in the scale versus the angle of twist. Then calculating the slope of that line, we will get the modulus of, that is modulus of rigidity. Tabular column goes like this. As I said, for each 2 degrees, we have to note down the torque in the dial for each 2 degrees. We have obtained the value like this after doing so. After that, we have to plot this diagram. Twist in degrees in x-axis, torsion in y-axis. That is whatever we have obtained in the table that we have to plot. So we have got this curve. The slope of this curve, dy by dx will give the torsional rigidity, that is modulus of rigidity of that material. It is similar to tensile stress, the test, but here we are getting modulus of rigidity. So this is the expression to find the modulus of rigidity. G is equal to T by theta into L by J. L is the length of the specimen. T by theta is obtained by the slope. L is the length. J is called the polar moment of inertia. It is given by pi into diameter to the power of 4 divided by 32, diameter of the specimen. Okay, then we will get J. We have to substitute that J here. T by theta is from slope, L is the length, J we have to calculate. Then we will obtain the torsional rigidity as 65.85 into 10 power 3 Newton per millimeter square. Now modulus of rupture, that is strength. Modulus means its strength in rupture. The torsion equation is given by T by J is equal to tau by R is equal to G theta by L. The torsion equation is T by J is equal to tau by R is equal to G theta by L. Using that equation, we will obtain tau. This is actually tau S is equal to T into R by J. T is what? The torque. The torque at rupture. Torque at rupture means the final value at breakage. Rupture means breakage. At breaking point, what is the torque? That and the original radius of the specimen divided by the modulus of rigidity, the polar moment of inertia, what we have found here, J is polar moment of inertia, that will give the measure of modulus of rupture. In the similar fashion, we have to find out the torsional yield strength. Torsional yield strength also same equation, but torque at yield point we have to take. Torque at yield point instead of taking torque at breaking point or torque at rupture. So then if we take torque at yield point, then we will obtain the torsional yield strength of the specimen, which is very important because sometimes yield itself is called failure for ductile materials, not up to break. We cannot wait up to breakage. If the material yields, then only it is the failure of the material. That is why yield strength or torsional yield strength is important. Hope you have understood. Thank you so much.
The experiment what we are going to conduct is called torsion test. In this torsion test, we are applying the twisting load on the specimen by using electrical motor. In this test, we are finding the torque, the what is applied on the material to the reference of how much the material is got twisted in the sense of how much it is. Here we are finding the torque with the reference of how much material got twisted. If we see the scale, we can see here one needle that we have to set manually at the initially. So from here we can see the scale with the least count of 0.1 Newton meter. So least count is 0.1, that means 1 division is equal to 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5. So one big line to second big line it is 0.5. So here it comes 1, 2, 3, 4, then 5. So reading goes like this. the specimen what we are using for torsion test. Initially we have to find out the diameter and the gauge length. Then we have to fix this specimen into the machine. If we see the chuck or the jaw or the holding device, see here inside there is a jaws. Inside there is a jaws opening and closing. So what we have to do, we have to fix the specimen into that holder. And here also if we see one point or the center drill we have done, that we have to fix it inside also there is a pointer, so that center drill or the pointer should match with each other. Then we have to tighten this jaw. That is one side clamping. Another side, if you see the second side of the specimen, there also there is a center drill. So inside the chuck also there is a pointer, so that pointer should match with the center drill. So we have to push this setup forward and we have to match this. We have to open the jaw. The jaw and we have to insert the specimen and we have to match the pointer with the center drill and we have to tighten the jaws. Both the jaws has to be tightened. This is the method of fixing the specimen. First insert one side, then match the pointer with the center drill, then tighten the jaw, then come to the second side, move the setup forward and match the pointer with the center drill, then tighten the jaw. Here we can change the scale for the, so we have changed the scale into 100 Newton meter. You can see we can change the scale setting. Now we have changed it into 100 Newton meter scale. Now it is 50. So for the experiment we required 100 Newton meter scale. So in that least count will change into 0.2 mm, 0.2 Newton meter. Initially we have to set the needle to 0. This needle moves only when the torque is applied. But how to set this one to 0? There is a fine adjustment here. With that we can set the needle into 0. Similar way, this also move it and place it here, touching to the black needle. And here where the degree, here also we have to set the initial reading to 0 with the reference pointer. Just to find out the twist on the material, just one line we have to draw here, so that we will come to know how much or the material is twisting or not. Just one line we have to draw with the chalk. That is optional. This line, it's not compulsory. Just to know the twist on the material, we have to draw this line. Rotate apply the load on the material by rotating the motor manually, by rotating the wheel. So degrees will move. At the same time, torque will be applied on the material. Torque whatever applied, that will be shown here in the scale. Now I am operating this. We can see here degrees will move. For each 2 degrees, we are taking the reading. If you see 2 degrees, it is moved here. We can see the torque applied. So here least count is 0.2. So 1 division carries 0.2. So 1, 2, 3, 3.8 is the torque applied for 2 degrees. So next, that is the first reading. Second reading, first reading will be 0. Initially both reading will be 0. Then the second reading is degree is 2 degrees. Torque applied is 3.4. Next again we have to take the reading for 4 degrees. So now next next the reading taken is 4 degrees, and here you can see the torque here. So similar way we have to take the reading till upper yield point. We have to move manually. Once the upper yield point crosses, we can switch on the motor. We can switch on the motor until the specimen breaks. Next, we are taking the reading for 6 degrees. So changes will be seen in torque also. Next for 8 degrees. So at one point needle will stop, it will not move further. So that point we have to consider as upper yield point. Next we are taking the reading for 10 degrees. We can see the needle is moving continuously. So 10 degrees over. Next we will go for the 12 degrees. So needle is moving continuously. At one point it will stop and it will not move. So that point we have to consider as upper yield point. So 12 degrees over. Note down the reading. Next 14 degrees. Note down the reading. Next reading will be 16. 16 degrees. Note down the reading. Similar way, next will be 18 degrees. So 18 degrees is over. Note down the reading. Next will be 20. So 20 degrees over. Note down the reading. Next 22. 22 degree over. Note down the reading. Next will be 24. Crossed. Note down the reading. 26. So if we see, it is taking some time to move further. So now it is stopped at one point. If you see the dial, it's not moving further. So whatever degree you got here, that on the dial, that we have to take, and whatever torque we have got here, that we have to consider as a upper yield point. So this is the reading you required the most in your experiment.
Password.
So we got the upper yield point. Now we have to continue the rotation here. So needle is not moving, it's taking time to move. So we have to wait. till it continue to move from that point. So degree is continuously moving forward. Still it's in the same position. So that point only we have to consider as upper yield point. Once the needle is moving further, after that we can use the motor for next readings. So we can skip some readings later. We can see here the twisting is started. We have applied that chalk. Because of that we will come to know that twisting is going on the material. Next, by using the motor we can take the reading. You can see this needle came back, so the position whatever we can see here, that we have to consider as lower yield point. This is the upper yield point, this is the lower yield point, because needle is moved slightly back. So again from that position it will comes forward. Consider as lower yield point. Again after that we have to switch on the motor. So this is the upper yield point. So needle will take some time to move further. The earlier needle moved back, that is the lower yield point position. So we can see the readings here. It's continuously moving forward. You can see now the breakage take place because of twisting force. So maximum load we can see applied here. You see the specimen, it broke at one end, because if we see the material, if there is a weakest point in the material, there material will break. If you see the material, it broke at one end, because where there is a weak portion, so on that portion only material gets cut. If the material is strength fully, it will break at the middle.